All right, the last concept in electrochemistry is looking at electrolysis or electrolytic cells. An electrolytic cell is not thermodynamically favorable. Therefore, because it's not thermodynamically favorable, we are going to have a cell voltage that is going to be negative, and also that equates to G being positive, and also K being less than 1. Now, because the cell is not thermodynamically favorable, it's not spontaneous, it will not occur on its own. Therefore, in the picture, you're going to see not a voltmeter, but instead you're going to see some type of power supply or battery. Something has to provide the electrical energy to propel the non-spontaneous reaction forward to make it react. Now, applications of this are things like electrolysis, in anything from like hair removal to even electrolysis of water into its gases, to electroplating, where we're depositing small amounts of metal on neutral metal atoms onto the surface of another metal to provide a band of protection from corrosion and other things. So, a couple things. I'm going to turn the page. So the normal type of problem on the national exam is whenever we have electrolytic cell, typically you're going to be utilizing this equation, which is the last equation on the green sheet, which we have not covered yet, which is on the bottom of your thermodynamics electrochemistry section on the green sheet. It's I equals Q over T. I stands for the current, which is the current that's coming in or supplied by the battery. Q is the charge in coulombs. Okay, what charge is being provided by, and time, little t is always time in seconds. So this equation allows us to convert the amperage, the current, or the charges into either other by using this equation. Okay, now again, Faraday's constant, which is F, on the green sheet it is written as 96,485 coulombs per mole of electron. But a coulomb is also defined on your green sheet as a volt is equal to a joule divided by a coulomb. So if I rearrange this, a coulomb is equal to a joule over a volt. The last lecture that I talked about this, right, I had Faraday's constant being in units of joules per mole volt. Well, we can see why. If I replace the C with a joules per volt, I get joules per mole volt. So it's the same thing, so you just got to be careful with the units here when we find these values. Okay? All right, so let's go ahead and do an example problem here to see how we can use this equation to figure out a certain concept. Calculate the number of grams of aluminum produced in 1 hour of electrolysis of aluminum chloride if the electrical current is 10 amps. Okay? Right away I see amps and I see hours or time. Well, if I look at the above, right away that's screaming to use the equation I equals Q over T. Okay? The T is 1 hour, but as I said, the equation says the time has to be in seconds. So how many seconds is there in 1 hour? Hopefully you said 3,600 seconds. Okay? The 10 amps is the current, which is the I value. So rearranging, I can find the Q, or the charge, by taking the amperage times the time. So 10 amps times 3,600 seconds. So the first thing you're always going to do in an electrolytic problem is to multiply the amperage by the time in seconds. Okay? In this problem, that is going to give us 36,000 coulombs. Okay? All right, now, because we have coulombs, we can now use, and this is why they have Faraday's constant in this unit, we can now use Faraday's constant to convert the number of coulombs into the number of moles of electrons. Why do we want to do that? Because if I know the half reaction or the balanced redox reaction, I can figure out how the number of electrons equate stoichiometry to the number of moles of that element. Because what I have here is I have aluminum chloride, which is aluminum ions and chloride ions because it's an ionic compound, and I have that being converted into aluminum. And you'll notice that in the half reaction, there are 3 moles of electrons produced for the formation of every mole of aluminum. So this electrolytic problems are literally, after we do the equation, figure out the coulombs, ends up being a stoichiometry problem. So there are 3 moles of electrons for every mole of aluminum that is produced by this reaction. And then 1 mole of aluminum has a molar mass of 26.98 grams. So if we go ahead and do the math and multiply throughout, we get a value of 3.36 grams of aluminum. So in 1 hour, we can plate out 3.36 grams of aluminum metal. Okay? All right, so I'm going to show you an example here. Immediately, I can tell that this is an example of an electrolytic cell because you want to look at right away at the top here. If you see a battery present or a power supply, those are words they've used in previous exams. If you see a source of electrical current or power, immediately you know it's going to be an electrolytic cell. If you see a voltmeter just simply reads the voltage of the spontaneous cell. So it's very important information to look at the diagram to see what you have present at it. If there is a power supply, you're already predicting that the voltage of the cell is going to be negative. Here's an example of the electrolysis of water, where we send electrical current into water. Again, we have an anode and cathode. And if we look at it, the 2 half reactions that take place in the electrolysis of water is right here. Water forms oxygen gas at one of the electrode, and at the other electrode, and it also produces hydrogen ions. Those hydrogen ions that are in the water can then at the other electrode be reduced to hydrogen. So this again is the reduction reaction because we see the electrons on the reactant side. And the other reaction is oxidation because the electrons are on the product side. Okay? But at one of the electrodes, we're going to see the formation of oxygen gas. At the other electrode, we're going to see the formation of hydrogen gas. So in both of them, you're going to see bubbles forming. Which electrode would you see more gas, more bubbles around? Look at the reactions and make that prediction. Hopefully you said the hydrogen. In the hydrogen, you would see twice as much gas being formed, twice as many bubbles, because of the fact that we're getting 2 to 1. Again, H2O, there's 2 molecules of hydrogen, 2 atoms of hydrogen for every oxygen. So the amount of gas produced for both diatomic elements is going to be twice as much for the hydrogen. Again, we can see that the water is being oxidized in the top reaction with 4 electrons. And the balanced equation shows the 4 electrons on the left side with the reduction. What occurs at the anode, oxidation or reduction? Again, vol. Oxidation occurs at the anode, and therefore the bubbles that are present here would be the oxygen gas. And the reduction reaction, the cathode, is going to be the hydrogen gas. So around the cathode, we would see more bubbles than around the anode, just because of the 2 to 1 ratio. The voltage of the cell combination, the 2 voltages, again, the oxidation potential. I have flipped this reaction from the table because it is written as a reduction, but as an oxidation, it's negative instead of positive. And the voltage of the hydrogen reaction is 0. So adding them together, we get a voltage of negative 1.229 volts. As we predicted, it's an electrolytic cell, therefore it's not spontaneous. So this reaction will not occur unless the power supply is turned on. If the power supply is turned on, then the electrical current will flow through. and we'll get the formation of the different substances. Okay, so again, identify the picture and see what we're looking for in this scenario. Do we see a power supply or a voltmeter? Okay, one other thing, electrical current still always flows from the anode to the cathode. Regardless if it's an electrolytic cell or a galvanic or voltaic cell, electrical current always flows from the anode to the cathode, no matter what type of cell that it is. Page here. And what I'd like you to do now is on top page 22, I would like you to go ahead and do the same example, and when you restart the lecture, you'll see the answer. But give it a try and see if you can figure out the amount of copper here, which is very much like the problem we just did, but it's copper instead of aluminum. Okay? So go ahead and give it a try. When you restart the lecture, the answer will be provided for you. All right, the answer ends up being 5.93 grams of copper. Hopefully that's what you got. It was the same exact steps to figure out the amount of copper just like we did. We took the equation, and I times T gives us the charge, the number of coulombs that is needed for this electrolytic problem. Dividing by Faraday's constant gets us into the moles of electrons. Copper 2 will transfer 2 electrons for every mole of copper produced. And then the molar mass gets us to our mass. All right, the next example. How long must a current of 5 amps be applied to a solution of silver to produce 10.5 grams of silver metal? Well, now we know the mass of silver metal desired, and we're trying to figure out the length of time. Hopefully you're starting to recognize that this is exactly the previous problem, but backwards. So I'm going to pause the lecture now. Why don't you give it a shot doing the same problems, but now backwards, to go from the mass of material to figure out how the length of time leading into this equation here. Okay? So go ahead and do that. Okay, if you haven't done it yet, I'm still going to show you the process. So 10.5 grams of silver. Okay, so by looking up the molar mass of silver, 107.87 grams of silver per 1 mole of silver. 1 mole of silver transfers 1 mole of electrons. How do I know that? I see the charge on silver is +1. So I only need 1 electron to make it solid state silver. It's a 1-to-1 ratio. Okay? And now applying Faraday's constant. All right, so going ahead and using Faraday's constant, we're able to convert the moles of electrons into coulombs. So we now go ahead and punch that in our calculator. I'm able to take the mass of silver and figure out how many coulombs of charge would be necessary to make this amount of electroplating out of the silver. So 9,392 coulombs. Again, the coulombs is the value of Q. The amperage is the value of I. So again, I equals Q over T. So rearranging this equation for T, Q divided by I will give us the time in seconds. So 9,392 coulombs divided by 5 amps gives us 1,880 seconds. This would be the amount of time it would take for this much silver to be plated out of a solution based off of the values. Okay, so it's literally doing the problem backwards. As I've always told you before, make sure you can do the reaction forward, but also the same type of reaction backwards. And that's pretty much it when it comes to electrolysis. Okay, with any electrolysis, if you have different combinations of reactions that you can add together, you still want to pick the 2 reactions that gives you the most positive value. Now, it's going to be a negative number, but if you've got 2 reactions and the voltage of that cell, one of them is negative 0.8 volts, and the other one has a cell voltage of negative 2.3 volts. The negative 0.8 volts is much more likely to occur, even at the power supply, than the negative 2.30 volts. So if you're asked to pick between multiple reactions as to which one is the most likely to occur of the combinations, you always want to pick the cell voltage that is the most positive. If it's an electrolytic cell, it'll be a negative value, but you want to pick the least negative or most positive of the combinations. Just like in a voltaic cell, you want to pick the combination that results in the most positive overall value. Okay? Last little concept here is right here. It says if I were to apply an electrical current and try to plate out copper metal, ions out of the solution, silver, and zinc, here are the redox reactions where the ions in the solution are becoming solid state materials. The voltages for each of these half reactions occurs. Based on these numbers, if I were to slowly turn up the electrical power supply and induce electrons into the solution, which of the three metals do you think is going to plate out first? Well, hopefully your eyes gravitate to must either be the most positive value or the most negative is right away what I'm hoping for. Right away we can already predict that copper is going to go in the middle. So who goes on either end? Well, even with electrolysis, which of these reactions is the most thermodynamically favorable? The silver or the zinc? And the answer is the silver because it's the most positive voltage. And this is only part of the reaction in this electrolytic cell. The other part is not known, but whatever it is, it does still add to an overall negative voltage. So because of that, silver is the most likely ion, okay, to come out of the solution and form solid silver, and then comes copper, and then comes zinc. These would be the orders of the ions reacting, and thus we'd expect silver metal to deposit on the electrode first, then copper metal, and then zinc metal. Okay, so that is electrolysis. We're looking at combinations of the cathode and anode adding to a negative cell voltage, and again, we'd use the same equations to calculate G and K from it, but that's something we've already done. It's just a matter of it's going to change and flip the sign. Okay? And that is the unit. So now go ahead and do the homework problem or two that I have online, and we'll start reviewing and getting ready for the exam in this unit.